Okay, you guys, I'm going to go through quiz 8 now. Quiz 8 was the problem where you had a ramp with some angle alpha defined on that ramp. You had a rod tipped up on that ramp connected to some incline, and that incline was at angle theta, and this rod made an angle beta relative to the ramp of angle alpha. And the question was, if this problem is in static equilibrium, if this bar is in static equilibrium, what are the normal forces, what's the friction force, what's the coefficient of friction, if only, let's change the color here, if only this surface had friction on it. So the bottom's going to have friction on it and the top is not, which is important because when we calculate our forces, this one over here will only have a normal force, while this one will have both a normal force and a friction force, which by construction will be perpendicular to one another. The friction force is going to be along the incline, and the normal force is going to be perpendicular to the incline. Okay, now I probably want to erase what I just did, so I'm not going to, I'll just undo it a few times. Wait a second. Undo. Okay, so the bottom one's the only one with friction on it, and we know if it's in static equilibrium that the sum of all the forces must be 0 in order that it's not accelerating. Oop, and let's change the color back to black. We know that the sum of all the forces in the x direction must be 0, and the sum of all the forces in the y direction must be 0. And we know that if we calculate the net torque about any point, it should also be 0. Put a vector here. Because the reason I put a vector here and not on these other ones is because I've already broken the forces up into the y and x components, so they're no longer vectors. They're now scalars in these directions. But in this one, I haven't told you in which directions the torque are. I haven't said it's like the z components of the torque or the x components of the torque. All I know is if I add up all the vector components of all the torques, they should add up to 0. Which means that the sum of all the x components, the sum of all the y components, and the sum of all the z components for all the torques should be 0. Right? Okay. So, if we know all the forces have to add up to 0, and we know all the torques have to add up to 0, then what equations do we need to write in order to confirm that that holds for this problem? Right? That's what we need to figure out. So first we start writing out what the forces are in the x direction. What are all the forces that could act? Well, let's just list those forces. It's good to identify what all the forces that act on the system are. So first, there's a friction force at the bottom. Just know that by FF. There's a normal force at the bottom. There's a weight force. And there's a normal force at the top. No friction force at the top again. That's everything. That's all the forces that could act. This plane is assumed to be, or this surface, which the incline rests, is assumed to be static. This wall supports this incline, so it can't move. So, we don't have to worry about the incline or the wall moving. Now we just need to start writing down all these forces. Now, a lot of you got confused by the geometry of this problem and introduced all these weird angles, all these weird definitions. It's not true that you can get away with just writing alpha, beta, theta. I mean, your final answer can always be expressed in terms of just the known quantities, but it will be useful to introduce one auxiliary angle, one angle that helps to describe everything else. But we don't need to introduce a whole bunch of angles. And the one that we're going to derive is going to be pretty simple. Okay. So in order to sum up the forces in the x direction, we first need to, so we'll do this first. This one, sum of the force in the x direction, sum of the force in the y direction, and then we'll do all the net torques. And if we have enough equations with enough unknowns with just those three, then we'll be all done. So first we need to figure out what the x direction means and what the y direction means. We have some really complicated angles in this problem, and so, if I look at the weight force is the only one that exists in the vertical or horizontal directions on its own. Everything else I'm going to have to break into components. The friction force, the normal force, I'm going to have to break those up into components. Now, because the friction force and the normal force are 2 out of my 4 forces, and they're both defined with respect to some angle alpha, it might be easier to actually write everything in terms of a coordinate system where x runs parallel to alpha and y runs perpendicular to alpha. But because we don't need to do that, and because that's kind of counterintuitive, and it doesn't exactly provide us a lot of advantage, and we could make a lot of mistakes running that route, I'm not going to do that. Instead, what I'm going to do is I'm going to do everything like usual. I'll define x to be positive in the horizontal direction. There we go. X will be positive this way, and Y will be positive this way. Those will be our two. Okay, easy. So now the weight force is going to be in the Y direction, and everything else is going to have both X and Y in there. Okay. So sum of the forces in the X direction. First, let's consider these forces in order. There's the friction force. Now the friction force is going to keep this thing from sliding down the incline, assumedly. We can assume that. So at the bottom, we have a normal force that acts this way, normal force at the bottom, and we have a friction force that acts up the incline. But the angle between the ramp and the horizontal is exactly alpha. So the friction force can easily be broken up into the X direction. Right, so the friction forces component in the X direction, so the sum of all the Fx's starts with minus Ff cosine alpha. Get a little bit better handwriting here. There we go, much better. And then we have to worry about next the normal force at the bottom. Now, because the normal force at the bottom is perpendicular to the friction force, those two are perpendicular to one another, I know that if I take the cosine of the friction force, I'm going to have to take the sine of the normal force, but we can justify that geometrically too. So if I look at this line, I know that this is horizontal. The angle between the friction force and the ramp angle is alpha. And the normal force is perpendicular to my ramp, so this is 90 degrees. So this angle here is 90 minus alpha. So the x component is going to be the normal force times the cosine of 90 minus alpha, which is the same as sine of alpha. So I have to add an NB sine of alpha. The weight force isn't in the x direction, so I don't have to worry about the weight force. And last, the normal force at the top. If you look at the normal force at the top, look at its geometry. It acts perpendicular to the incline there. So here's angle theta. So the angle between perpendicular and the ramp, that's theta. This is 90 degrees by construction. So the normal force at the bottom. The normal force is perpendicular to the ramp, so I know this is 90 minus theta. I know this is 90, so this is theta. So the normal force times the cosine of the angle is another contribution, the normal force times the cosine of theta. But because it acts down and to the left, I have to subtract it. And the cosine theta. And that's all our forces, so that's 0. How many unknowns do we have? 1, 2, 3 unknowns. So we better find 2 more equations. Sum of all Fy's. Okay, first the force due to friction. Well, it's going up and to the left, so up positive, Ff sine of alpha. Normal force at the bottom, it's up and to the right, so it's up, it's positive, NB cosine alpha. I'm just looking at the previous equation and changing sine for cosine wherever appropriate. mgx straight down, so minus mg. And the normal force acts down and to the left, so it's going to be minus NB sine theta. That's 0. Lastly, how many unknowns do we add? Well, we know the weight force. And, I made a little mistake here. Sorry about that, you guys. I keep writing NB where I mean NT. Sorry. Bottom, T means top. Oh, maybe I should make a whole new video now. Should have been obvious, I guess, because it involves theta, not alpha. But it's good to be right, so let's be right. My bad. Sorry about that, you guys. Okay, and now I need the sum of all the torques. Over here, a little bit of space. So how many torques act? Well, it matters where you go, right? If I go here at the top and try to calculate my torques, I'll need to consider the weight force and these other 2 forces. If I go where the weight force is acting, then it doesn't exert a torque, but these 3 other forces will exert a torque, the 2 on the bottom and the 1 on top. So if I go here at the bottom, I eliminate 2 out of my 4 forces. And all the vectors that get me to the forces, all the vectors that get me to the point where the forces are acting are all the same. They're all along this line. So it's easy to write this one. So I'll just sit at the bottom. I'll write the torques from those 2. Now, the weight force is going to try to get me to rotate this way. The normal force is going to try to get me to rotate this way. So hopefully they have different sign, but we'll figure that out. I mean, it might depend on how this thing is tipped and how this thing is tipped, exactly whether or not the normal force ends up like pushing me this way or pushing me this way. But you know, there should be a difference between those two. Anyway, we'll see. Well, I don't know what should happen actually, but that's something to think about. If it's ever obvious to you that two torques should oppose one another, make sure that there's a sign difference in your answer. Okay, so now we'll solve it. So the sum of the torques in general goes is the sum of all the distances to the places where the forces act. So we have a sum of all the r cross f's, where each r cross f corresponds to one torque from one force. If we sit at the bottom, there are only two forces. There's the weight force and there's the normal force at the top. So starting with the weight force, so I can rewrite the sum as the vector that gets me to where the weight force is acting, crossed with the force vector due to the weight force, plus the vector that gets me to where the normal force at the top is acting, cross with force, the normal force at the top. We'll just put the vector in here, or FNT, make it a vector. The force due to the normal force at the top. We know all these should add up to 0, right? Because all this, the net torque should add up to 0. So first, what's RW cross FW? Well, RW is the vector that gets me from the point where I'm calculating the torque at the bottom to the place where the force is acting. And it's not exactly obvious from the beginning how to write RW relative to my coordinate system, right? So like the vector that gets me to the point where the weight force is acting, so let's just plug here. Alpha, this is beta, and this is the ramp. It's not clear exactly if I want to break up the vector that describes the ramp angle, what this angle is. It's not given to me. It's not beta, it's not alpha. But I know that this angle is pi, so I know that pi minus beta is this angle. I also know that the angle between the horizontal and the ramp angle is alpha. So the angle phi that denotes the angle of the ramp, of the bar relative to the horizontal, phi equals pi minus beta minus alpha, or you could write it as pi minus beta plus alpha if you put it in parentheses. It doesn't really matter, but that's what it is. So that's a useful angle. But that's the only other auxiliary angle we need to introduce in this problem. All the other problems are given to us. And note that phi is expressed in terms of the known quantities beta and alpha. So it's not really an unknown. It's a useful angle because we don't want to write pi minus beta minus alpha everywhere. It's a useful angle, but it's not necessary. We could write everything in terms of pi minus beta minus alpha. Just knowing that you have this information is really important. Okay, so now we can describe what RW is. RW is L over 2. I go L over 2 along the length of this rod times the cosine of phi in the x direction plus the sine of phi in the y direction. That's the vector that gets me to where the weight force is acting. And what's the weight force? Well, the weight force, I'm crossing it with the weight force. The weight force is mg in the minus y hat direction. Okay. Now, the way we cross vectors, vector crossing is it's distributive over multiplication. So this is really L over 2 mg times the cosine of theta x hat cross, and I'm sorry, my x looks like I'll put like maybe a bar over it to make it like a cross or something, I don't know, just a different symbol. Cosine theta x hat cross minus y hat plus sine theta y hat cross minus y hat. But y hat cross y hat or y hat cross minus y hat is just, it's a vector in one direction crossed with itself, so that goes away. That's 0. And x hat cross y hat is z hat, so this minus sign just gives me a minus z. And so this torque is minus mg L over 2 cosine theta, and of course, where I meant theta, I meant phi, damn it, cosine phi in the z hat direction. That's one torque. What's my other torque? My other torque is RNT cross FNT. The vector that gets me to the normal force at the top crossed with the force of the normal force at the top. The vector that gets me to the normal force at the top is L times cosine phi x hat plus sine phi y hat. That's the vector that gets me to the top. This is RNT. What's FNT? FNT is the vector that describes the normal force vector at the top. So it has a magnitude of NT, and its direction is determined only by theta. Its x and y components are only determined by theta. I can say that this normal force is NT big, broken up into minus cosine theta in the x hat, minus sine theta in the y hat. Okay. Now I'll leave it as an exercise for you guys, but if you cross RNT with FNT, you actually get NTL times cosine theta sine phi minus cosine phi sine theta in the z hat direction. And using a trig identity, this is NT times L, so a force times a length, which is a torque, of sine of phi minus theta. So these are our torques. No new unknowns. We're only using NT, and here there are no unknowns. So our net torque equation at the end of the day, erase some stuff. Make this erase a little bit bigger. So I'll erase my net torque. So I'll use this information now. The net torque at the end of the day is 0, and it's NTL sine of phi minus theta minus mgl over 2 cosine phi. All that is in the z hat direction. But since this vector, right, since this net vector must be 0, it must be the case that this is equal to 0. So now we have three equations. We have three equations. 1, 2, 3. With three unknowns. The normal force at the top is easy to solve for because this is a constant, and we know what L and sine phi minus theta are, so we can solve for NT immediately. Once we have NT, then we can go back to, for example, well, I guess you'd have to go back to both of these two, because both these two equations have all three variables in them. But now you can do some substitution and figure out what the values of FF and B are. That's the end of the sentence, I guess. And once you know what FF and NB are, you can figure out mu, coefficient of friction at the top, by taking the force of friction value divided by the normal force at the bottom. Because mu tells you how the force of friction relates to an applied normal force. So that's the solution for week 8. Remember, start with the net forces being 0. That's easy. And then write as many torque equations as you need in order to solve the problem. In this case, one torque equation was enough to get me 3 equations and 3 unknowns, so I was done. If I needed more equations with more unknowns, then I would add them. But that's it. Okay, you guys, I'm all done. Ask me any questions you want.